Okay, so today I'm going to talk a little bit about our next set of labs, which not only use the um, analog to digital converter that we talked about before, but we're talking about the next chapter, which is the digital to analog converter. So we're going to go sort of backwards from what we had done before. We basically will have two labs that sort of concentrate on using the digital to analog converter. So the first part that we're going to talk about is just the hardware aspect. How do we do digital analog conversions? Because we talked about the analog to digital converter with the successive approximation converter. So this time I'm going to talk about the opposite. How do we go from digital back to analog? Okay, obviously the purpose of this is to convert digital values back into analog values. And so it's the opposite or inverse operation of the analog to digital converter. And so our output voltage is going to be related to the digital value that you bring into the digital to analog converter. Now one thing I'll point out, as I'll point out again soon, is this reference voltage is important because whatever digital value that you have is going to be converted to some analog voltage, but it's going to be based upon that reference voltage. So you change the reference voltage, the outputted analog voltage will change as well. So make sure you realize that that's going to happen, and it, of course we'll talk a little bit more about that as we do the lab. There's multiple types of digital to analog converters. There's the binary weighted resistor, the R to 2R ladder. There's what we call this multiplier digital analog converter and non-multiplier digital analog converter. In the multiplier version, the reference voltage is constant and it's set by the manufacturer, so you can't change it. So that previous slide where we talked about the output voltage, it's always going to be related to that same reference voltage. The non-multiplier DAC will not have that case. So characteristics of these digital analog converters, well, as you'll see, you can use you can get them op amps, switches, resistors, whatever, and typically we provide something that is based on those resistance values. Will give you something related to the significance of bits, and you'll be able to manipulate that if you're doing the actual digital to analog converter. So here's the simple one, and this is just called the binary weighted resistor. And notice here, this is very similar to the op amp circuit that we've done before. And if we just look at it ideally, let's see what happens here. Okay, here we have V plus equals 0 for the ideal op amp. And then that gives us the ability to write this equation here. We can say, notice that it says this Vref is down there, but I can say V minus, well, maybe let me do it over here to make it a little bit more clear. Let's say VLSB is here. V, I'm just going to call it NSB. And then VMSB. And then I'll say VNMSB. So I could write an equation, and this is just to sort of give us an idea of what's happening here. We have V minus minus VLSB over 8R plus V minus minus VNSB over 4R plus V minus minus VNMSB over 2R plus V minus minus V MSB over R. And that's, sorry, I'm going to have to write over here. So that's the current leaving here, going there, 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 and there. And then I need to do the other current, so I'll just say plus V minus minus V out over R. And we could say just RF like it has, but notice that RF is equal to R. And that sum of those currents is equal to 0. So then when we set, because V plus equals V minus equals 0, what happens is we get minus VLSB over, I know this is messing with my PowerPoint here, it wants me to do something else. So I'll just get rid of this term, this term, this term, this term, and so I'll get that. And notice that this can all be, if this is this way, we can move the V out over RF over here, and then if we solve for RF, solve for V out, so I can move this RF to the other side of the equation, so I'll have RF, and I'm going to put these here because this is a multiplier now, not subtracting off. And so the output voltage is equal to that. And now note that these voltages, this VMSV, VNMSV, they're either minus Vref or 0, right? Because if the switch is going in the scenarios that they show right there, it's one thing, but if the switch closes here, it's connected to ground. So basically, each bit is either tied to the reference voltage or tied to ground. So that's basically telling you one thing, and that is whether or not that bit is that bit is affecting the output voltage. So if RF is equal to R, and we have this filled out in a little bit better way, we can say this is going to be minus VLSB over 8 minus VNSB over 4 minus VNMSB over 2 minus VMSB over 1, I'm just going to put that there, equals V out. So you can clearly see that the most significant bit is going to have that reference voltage. If that bit is set, that reference voltage is divided by 1. Now of course this minus sign gets rid of all of the minus signs there, so if I put it here like this, I can say this is going to be like plus VLSB, or maybe I should say plus Vref or 0 divided by 8, but it's related to this most significant, I'm being backwards here. This one is this term right here, and if minus Vref is tied to there, then I'm going to get minus a minus Vref over 8, so Vref over 8, but that depends on if this switch is set there. So if the least significant bit is a 1, basically, then I'll put that switch tied into the 8R. If it's not 1, if that bit is a 0, then that switch gets down here and we're tied to ground, so we don't have that. So the output voltage basically gets added. The most significant bit is here, so the next most significant bit this one here is divided by 2. The next most significant bit after that is divided by 4. The next most significant bit, or the next least significant bit, is right here, and that's divided by 8. So these resistor values are what determines the order in the bits. So this is just a 4-bit one. Obviously, if we had a 5-bit converter, then we need to have a 16R. If we had a 6-bit, we need to have a 32R, and so forth. Now, I hope this allows you to understand how you'll get the output voltage, and the switches are basically based on whether the bits are 1s or 0s. But the problem with this digital to analog converter is it's very dependent upon your selecting these resistor values carefully. Now, obviously, you could use potentiometers or variable resistors to help you with that, but it's very sensitive to all of these, especially as you start getting, these resistor values that are starting to be divided by a more higher and higher number. That's going to get you out of the ordinary operation of the op-amp if you're not careful. But anyways, the process is very simple, and that's how the digital to analog converter works. So anyways, this is just telling you a little bit more about sort of those switching. So if you had 1, 1, 1, 1, and this talks about the set and cleared part of, if you have the 0, then the switch needs to be in that position. But how you would get 15 out, and then if you had that, that would give you, in this equation you would get, Vref over 1 plus Vref over 2 plus Vref over 4 plus Vref over 8. And that would basically be giving you the output voltage there. Notice that, what's going on here is each time you do this, the weight in each particular branch, like this branch is going to have a current I, but the current in that branch is going to be half of that, and the current in that branch is going to be half of what was in this branch, and the current in that is going to be half of what was in this branch, because the voltage here is, well, maybe I should be careful and say that's if there's a 1 selected to each one. Obviously, the branch changes if I go to 0, because then I'm going to have something minus 0 over that resistance. But the idea is if you have the switch set on, each consecutive branch will have that current factor reduced by 2. And this just basically shows you the overall idea, and that's the equation that I came up with before. I thought I would go through the actual analysis and where that came from, because sometimes I think it can be a little confusing because you all have not seen op-amps all that much in electronics class. So this basically tells you what can happen if you have a higher resolution, gives you the formula for it, and so forth. The R2R ladder is a little bit different here, but you can already see why this one might be better than the other scenario. Look at what the values are every time. They are either 2R or they're R. And that's a big improvement, right? Because that means all your resistor values are of the same magnitude, basically. Like if you're using 10 kilo ohms, then 2R would be 20 kilo ohms. And you're never varying from those values. Whereas the other ones, if you started off at 10 kilo ohms, then you'd have 5 kilo ohms, then you'd have 2.5K, then you'd have 1.25K, and so you start rapidly getting problematic numbers as you start getting more bits. So I highlighted that before, but here's where you can see that it's important. And so this is quite similar, but notice it's V plus equals 0. So that's going to make V minus equal to 0, and we can still write that same kind of equation. So if this is V minus here, I can say minus V MSB well, let me be careful just to make sure you see where it comes from. So I'd have V minus minus V MSB over 2R plus V minus minus, okay, now here's a difference though. I'm going to have to call this V, I don't know what I want to call it. I'm just going to call it V1 for right now. So V minus minus V1 over R plus, I'll call this V2. So I've basically summed those two currents. Oops, forgot one. Plus V minus minus V out over 2R equals 0. And then I have to write the equation here, which will be V1 minus V minus over R plus V1, and let's just, so this one only has 3 bits basically that we're looking at here. So V1 minus, I'll call this minus V NMSB. So I'm doing this current here, V minus minus V NMSB over 2R plus V1 minus V2 over R, so it's this current, that's equal to 0. And then I've got to do my nodal equation right there, so that's V2 over 2R, because that's V2 minus 0 over 2R, plus V2 minus V LSB over 2R. That's the current going this way, and then of course the current going back across that way, that is V2 minus V1 over R, and that's equal to 0. So obviously the more bits you have, the more kinds of things that you're going to have right there. And notice that this VMSB, VNMSB, and VLSB are either, in this case, VREF or ground. So obviously it's a little trouble to solve this one. I can, get rid of my V minuses because V plus is equal to 0, so I can come back here and cancel like all of those out. And then the pathway will be I need to solve for probably the easiest way to see it is solve for V2 in terms of V1 and VLSB, and then plug that in here, and then solve in right there. Then I'll have all of V1s in a VLSB and a VNMSB. So then I can solve for V1 in terms of VLSB and VNMSB. Then I can substitute that into this term, and then I'll have something with V out in terms of VNMSB, VLSB, and VMSB. And so that's what I want, and I can get that final equation that I'm looking for. And so basically what happens here is you can see it says the same input switch setup as the binary weighted resistor DAC, but all bits in this case pass through a resistance 2R. So what they're trying to show is this one goes through 2R, this one goes through 2R, this one goes through 2R. And then it says the least significant the bit, the more resistors the signal must pass through. So what that means is you got that 2R, but then it's got all this junk here, 2R and all this junk here, and so it's got to pass through more resistance. So it's basically doing the same thing that we were before, and it's dividing that current by 2 at each node. And so it's a sneakier way, but you end up with the same kind of question. And so here it's trying to show you that current divider happening as we look at the particular circuit. And notice in this case it's showing you 0, 0, 1 being your input, and so the voltage Vref is set there at that lowest bit. These are both tied to ground, and so that's going back and looking at this one. That is putting Vref tied into this one, leaving those two tied to ground. So this is ground, this is ground, and so I think maybe the easiest way you can take it from mine is you can say, okay, in that case, my V2 equation that starts right here is going to have my VLSB being Vref. So I will have taking this equation, I will have an easy way to solve it is to multiply everything by 2R, and so I can write this as V2 plus V2 minus, now this, as I said, VLSB is Vref, and since everything was multiplied by 2R, that still, that cancels with the 2R that's in this denominator, and then multiplying this by 2R will give me a 2 out front, so I get plus 2 V2 minus 2 V1 equals 0. Okay, so now I just have to, do my addition. I'll have V2 plus V2 plus 2V2, so that's 4V2 equals 2V1 plus Vref. Now I can say V2 then is 2V1 plus Vref over 4. And of course that makes sense, right? We have the 1's bit, the 2's bit, and the 4's bit. So we know this is the least significant bit, so this is the 4's bit, so that sort of makes sense to us right there. Then I'm going to plug that into this part right here. I'm also going to multiply everything by 2R again. So now remember this first thing right here came, I was looking at it, this first term. It's like, where did that come from? And I'd forgotten. That's V1, that's the current going this way, V1 minus V minus over R. And since that V minus was 0, it went away. So anyways, if I look at this entire equation right here, then that's going to give me, if I multiply by 2R everywhere, then that's going to be give me 2V1 plus, okay, the next one is going to be V1 minus V in MSB. Well, we said that was 0 because we were tying that V in MSB to ground in that case. And then the last one is plus V1 minus V2 over R. So again, multiplying by 2R, that'll give me a 2 there. So I'll have 2V1 minus 2V2. So 2V2 is going to be 2V1 plus Vref over 2, since it got multiplied by 2. And that whole, I'm running out of space here, but that whole thing is equal to 0. So that'll give me 2V1 plus V1, so that's 3V1, plus 2V1 is 5V1. So 5V1 and that's that term, and that term. And then I'm going to have minus V1, because one of them subtracted off there. Notice that nice algebraic way it's going to work. So that's 4V1. And notice, let's be careful there, that's this whole thing was minus V2. So I better be careful and realize that that's that way. So minus Vref over 2. And that's equal to 0. So this gives us, if I move this up here, that gives me 4V1 equals Vref over 2. So then I can plug that in my last equation, which is this one, and I'm going to put that up at the top here just to make sure we see it okay. Remember, VMSB now is also tied to Vref, because we were only doing VLSB is equal to Vref in this one because we were trying to do the conversion of 0, 0, 1. So if I do that, I can come back here and I can see that I've got, okay, this is going to be multiplied everything again by 2R. So I'll have minus a 0 times 2R plus a minus V1 over R multiplied by 2R. So that's minus 2V1. And then minus V out over 2R multiplied by 2R is going to be minus V out. And that's equal to 0. Okay, so V out is going to be equal to 2V1, which is equal to 2 times V1, which from this equation right here, notice V1 is Vref over 8. So this is Vref over 4. And that's what we expected, right? Because we have the 1's bit, the 2's bit, and the 4's bit. And so if we should either get Vref over 2, or Vref over 4 if we have a 3-bit number coming out and needing to be added to the output voltage. So this is the same process. And now notice this is just sort of showing the current divider approach from it, but I hesitated to show that directly because you can look at it and you can see what happens. Basically what's happening in this is we have an R and an R here that's in series, so that's 2R. When you look at that, it's going to be in parallel with like this 2R right here, so that's where this current would get divided into half going this way, and then okay, we combine those into 2R, just thinking that this is a short right here. So this is 2R and 2R in parallel. That combo together is just R. That would be in series with this R, so those two in series would give you a 2R for this entire branch. That 2R in parallel with this 2R is again R. So you can see what's happening is each time we come into a branch, we basically see the same resistance in that branch going, to the left as we do going down. So if we see the same resistance in each branch, then the current will go into half of what it was. So this is the idea of what's going on this, and notice here it does say the op-amp input is ground because V plus was equal to 0, so this is basically the V plus equals V minus equals to 0. And I think maybe you can understand what's going on now with this, but it's harder to see at first because you all don't probably have quite enough experience with current divider. So anyways, this is the result of what happens, and you can see the same kind of thing happens right here as we had before, and we can get our bit pattern to do everything that we wanted as before. So one of the things you can look at here is if you look at this particular thing, you can sort of get if RF is equal to 6R. If you look at this output resistance right here, you can kind of have the same thing that you had with the binary weighted if you look at the overall formulas. Where you have the currents and the output voltage. Here's another example. We could go through it again. I don't really think it's all that big of a deal to go through it again, but you can see that this is what you would get if you had 101. So the number 5 and your reference voltage was 10 volts, and your resistor values were this particular thing. You can see we've set the least significant bit tied to Vref and the most significant bit tied to Vref, and in this diagram make sure you realize that's this one and this one respectively, and you can go and use those equations and find out that the output voltage would be 4.17 volts. Now remember, with the digital to analog converter, you're converting a particular digital value to an analog voltage. So you have this same kind of resolution. You can't get any analog voltage that you want out of it, but the more bits you have to use, the more discrete levels of output voltage you can get. So anyways, the ideas behind these two different digital to analog converters they're sort of similar. The pros of the binary weighted, I think it's the easier one to understand. The con is that you really aren't going to have much ability to do higher than 8 bits because of those resistor problems that we talked about. Has a large number of resistors. I didn't really talk about susceptible to noise, but that's again going because that's again related to this constant. If you had 10K, you need 10K, 5K, 2.5K, 1.25K, and so forth as you start making these resistance values smaller and smaller by half each time. That doesn't happen with R to 2R, and it's I think really a whole lot easier to implement in terms of the resistor values you need, which thus makes it easier to manufacture. And so the analysis is more confusing, that's the main con, but you can imagine which one is used more often, this one, because once you understand the analysis you can sort of get it from there.